So we like to start with a thought of the day. Today's thought of the day is from Primo Levi, who says the aims of life are the best defense against death. That is, the aims of life are the best defense against death. Now, what does this say to you? Have a think. But for me, what this essentially says is that we should do all we can when we can, because tomorrow is not guaranteed. And if that is what it means to you, then let me save you time by going on. P.S. Don't forget, if this says something else to you, comment below. Okay, so who is this for? This technical system building block series is for technical program managers or system product engineering managers, engineering leads, anyone really that's involved in the tech ecosystem. What will we cover? We'll cover a range of building blocks. Initially, the first four will look at domain name systems, load balancers, databases, key values stores, and then in subsequent episodes we'll look at the rest. Something that may not be immediately apparent is that currently right now in the UK there's a skilled workers shortage, right? Particularly for in-demand roles across technology, banking. And my hope is that these series of talks will help, in some way bridge that gap, right? So if you like detailed one-to-one coaching sessions, comment below, reach out on my handle. It's going to be below here. Reach out to my handle and I will be happy to take you through a one-to-one personalized tech training plan. Yep. So right to the topic of the day, domain name systems. I think we can start by asking a simple question. How do we find things on the internet? Generally, there are a few ways you can do this. You can use addresses or locations that specify where something is, just like with a physical address. We may still need a map to get the address, but on the internet, addresses are typically IP addresses and routers know the maps. Another way you can find things is by using names, right? In particular, if you consider domain names or um, domain names, these are sort of like unique names that identify websites. They are mapped onto IP addresses based on a lookup service that uses a database. Now, the most well-known lookup service, and there are others, by the way, is the DNS or domain name service. So, for example, when you enter the URL educated.io into your browser, it uses the DNS to find the actual IP address of the server that hosts it. Another way you can find things on the internet is content-based addressing. So this is when you use the content, you do a search for a content and use that content to identify what you're looking for. Yeah. A way I like to think about this is that the domain name service is sort of like a phone book, right? So imagine a phone book. You have the caller, you call someone, and you check. You either update your phone book with records when you meet someone new, or someone you've known for a while, or you change your numbers, and then you read from that phone book, right? And then person A will have these numbers, person B will have that number. Or you can, in much the same way, the caller in this sense for the internet is the client, so that's your mobile phone, desktop, whatever it is. And then the website is what you're trying to call. You send a query, you get request to your domain name server, and then you get a response. And for something like educative.io, which is one of my favorite learning platforms, that is the actual IP address. So that's the IP address equals to the phone number, and then the domain name system responds by reaching out to that phone number. Yeah. So in summary, if you consider the example of a mobile phone where a unique number is associated with each user, to make calls, you can initially memorize the phone numbers, or as the number of your contacts grow, your phone book expands or explodes, depending on who you are. You have to use a phone book to keep track of, all your contacts. This way, whenever you need to make a call, you refer to the phone book and you dial the number. That's essentially what I described for the internet. Yeah. So in summary, DNS is the Internet Naming Service. It maps human-friendly domain names to IP addresses. Resource records, those are the smallest units of information that you can request from the server. Example, CNAMEs, MX, NS. Caching is important just because it reduces the need, and I will discuss this later on. But as a summary, it reduces the burden on DNS because then you don't have to, because then if for frequently requested sites, they just come, depending on where the cache is done, you can easily access that, reducing latency and also simplifying. So just using the educated of IO as an example, the user will request a visit to a website. You enter the URL in your browser, and then the browser will request that the ISP, Internet Service Provider, forwards the DNS query to resolve the request. Then the ISP forwards the DNS query to the DNS infrastructure. That's the forwarding query here. And then you get a response back, which is a list of IP addresses against that particular domain name. The IP addresses reaches the browser back, and then the browser now sends the HTTP GET request on the received IP address. The ISP then forwards the HTTP request to the web server, and then you've essentially received, the loop is completed and you've received your data. So what is DNS hierarchy, right? The domain name system is not a single server that accepts requests, or else that would be a tremendous problematic bottleneck. It's actually a complete infrastructure with name servers at different hierarchies. There are mainly four types of servers in the DNS hierarchy. So there's the DNS resolver, which essentially initiates the querying service and forwards requests to other domain name servers. Typically, DNS resolvers lie within the premise of the user's network. So imagine if you work in a company or a bank. So within that network, that DNS resolver typically will reside there. Then there are root level servers. These receive requests from local servers. They maintain name servers based on the received request. And then they typically own those top level domains. So if you'd have seen .com, .edu, .us, .mail, .gov. Those are the root level servers. Top level domain servers, these hold the IPP addresses of the IP addresses of the authoritative servers, and then the authoritative name servers. These are the organization's DNS name servers that provide the IP addresses of the web or the application servers, right? So now, unlike Unix servers, which are processed from left to right, just to point that out, DNS name servers are processed from right to left, right? So if you imagine your whatever.com, you first process the .com and then process, okay? So this essentially shows us the different, so that's the root server on top, the top level domain servers, .com, .edu, .io, .org, this is an example for educative, and then the authoritative server, okay? So something else is an example of these root servers. You can see them here: IO servers, edu server, .com servers. These are top level domains. Then the second level domains like facebook.com, amazon.com, etc. So a word on caching, right? Which is a key part of making this work, right? So what is caching? Caching refers to the temporary storage of frequently requested resource records. And a record is a data unit within this domain name system database that shows name to value binding. So an example is a user requests a visit to a URL. The browser has cached the data, right? Now, what happens if if there's a cache miss, in other words, the browser hasn't cached the domain to the IP address mapping, what happens in that situation, right? It checks the next hierarchy. Remember we said that there were four levels. Maybe there are four levels of hierarchy. So it will check the OS, right? Check the operating system to see if um, the DNS resolver can resolve that. Maybe stored in the operating system. If the OS doesn't, it goes again. So there's a cache miss from the OS. It goes to the local domain, the local DNS server. If that also doesn't have the mapping, then it will check the ISP to see if the ISP has that. And then if the ISP, if there's still a cache miss from the ISP, it goes on to the DNS infrastructure, which will definitely have it. And then from DNS infrastructure, the loop starts to go back. There's a reply from the DNS infrastructure, and at each time as the response is going back through the different layers, it will be updated all the way. And then the browser will now have the updated cache so that the user request subsequently, if you go there, if you click on the same link, for example, educative.io, you will have your request served locally. So although the DNS hierarchy facilitates the distributed internet that we know today, it's a distributed system itself. Okay. So there's advantages of having it as a distributed system. It avoids a single point of failure. If you just had only one local system, you can have low query latency because users can get response from nearby servers. And at some point, one of the building blocks we'll talk about will be the content distribution network. So as you can see the benefits of having servers that are nearer to your client. Um, and then it gets a higher degree of flexibility during maintenance or upgrades. Because don't forget that all these tech systems, they need to be maintained, they need to be updated. So when it's being updated, when it's being maintained, because you have a distributed system, it's a true replication. I'll discuss about things like that later on. You'll still be able to have a cache hit, or you'll be able to receive the URL that you request for just because it's distributed. So that means there's duplication in the system. Now, just to say that there are 13 logical root name servers, named letter A through M, with many instances spread throughout the globe. The servers are managed by 12 different organizations. Now, I think let's just talk about some of the elements, right? So how is the DNS scalable? Well, it's scalable because there are roughly 1,000 replicated instances of 13 root level servers spread throughout the world, and they're strategically placed to handle user requests, user queries. Labor is divided among these TLD and root servers to handle queries, and then the authoritative servers themselves are managed by organizations to make the entire system work. So it's like everybody comes together to make DNS work. In terms of reliability, there are three key components to the DNS and reliability. The first is that there's caching, which is done in browser, is done in the operating system, is done in the local name servers, and then the ISP's domain name system resolvers also maintain a rich cache of frequently visited services. Now, even if some DNS servers are shut down, maybe for maintenance, I said, cached records can be served to make the DNS still a reliable system. There's server replication. So there are replicated copies of each logical server spread across the globe so that user requests can be entertained at low latency. Redundant servers help improve the reliability of the system. Then also, another thing that ensures reliability of DNS is the protocol, right? So now many clients rely on the user datagram protocol UDP, which you may know is unreliable, but it's important to acknowledge that the UDP has its use because it gives some distinct advantages. So for instance, it is faster, therefore it improves the DNS performance. Internet service reliability has actually improved since the internet, has improved over the years, and UDP typically is favored over TCP. But something that I would also like to say is that UDP queries or DNS queries, sorry, DNS queries are usually transmitted at the transport layer. So if there's no response, the request response. So if there's no response, there's typically you may need an additional round trip, but at the end of the day, the UDP still provides a shorter delay compared to TCP. Okay, because if you recall, the TCP or Transmission Control Protocol, it requires a three-way handshake before data exchange. In terms of consistency, um, DNS uses various protocols to ensure consistency um, and to ensure for the update and transfer of information among the replicated servers in the hierarchy. Um, Something that is good to know is that DNS compromises on strong consistency to achieve high performance because data is read frequently from DNS databases compared to writing. So there's a higher read. So the read to write ratio is high. So what DNS does is it provides eventual consistency. In other words, performance and availability is more important than consistency, right? Also, we mentioned caching, but sometimes you can see that as a result of caching, consistency can suffer. So what happens is authoritative servers are located within your own or the host organization, which ensures that certain resource records can be updated without having to ping the DNS hierarchy itself. Something else to maintain high availability is that there is a low or small time to live. This reduces downtime. So if any server or cluster fails, the organization can update the resource records right away. You will experience non-availability only for the time the TTL is not expired. But if the TTL is large, the opposite situation, then you see that the organization will update its resource records over time, and then you keep on pinging an outdated server, which is not good. So for consistency, you want to have a small TTL, and that's essentially what. Um, okay, so this brings us to the end of the first of our systems, building block systems. We have looked at the domain name system. We have considered the different levels of the hierarchy. We've described how consistency, availability, performance is achieved. We've discussed caching, which is important because even for database, caching will pop up in lots of different places. As usual, like, subscribe. If you have any question, don't forget to let me know. Take care. I will see you in the next discussion, which is going to be about load balancers.